In this lab, we're going to determine the sum of two vectors graphically and mathematically. We're going to use both the head-to-tail method and the component addition method. The first part's about the head-to-tail method. I'm going to demonstrate the process of the lab using these two vectors, A and B. If you're doing the lab yourself, then you'll actually want to use different vectors which are at the end of the lab. So this is your vector A and your vector B. The first thing we want to do is measure the length of each vector. That's often called the magnitude of the vector. So for vector A, the magnitude is going to be the length of it. So what we should do is place a ruler along the length of vector A and record its length with uncertainty included. I'll do that now on my paper. So I get that the magnitude of A from my paper is 4.56 centimeters, and then I'll say plus or minus 0.05 centimeters. Next, I'll place a ruler along the length of B. So that could look like this. I get that B's length is about 5.52 centimeters plus or minus 0.05 centimeters. Now that I have the lengths of A and B, I need to find their angles in standard position. We'll call that theta A and theta B. So what I'd want to do is place a protractor down on top of the vectors so that I can measure the angle of A, which is the blue here. It looks like it's between 35 and 40. I'd say 35.2 plus or minus 0.5. For theta B, we need an obtuse angle, an angle that's bigger than 90. Here's 90 degrees right here, and we have to go just a little bit farther beyond 90. This is because standard position angles have to be measured from the positive x direction. Just like in math, the unit circle starts with 0 degrees and then goes to 90 degrees and then 180. This is the convention for physics as well. When we're measuring standard position angles, we want to do it counterclockwise from the positive x direction. So I get that theta B is 112.6 plus or minus 0.5 degrees. Now that I have these measurements, I need to construct my own drawing on separate paper. And the directions say to arrange vector A so that its tail is at the origin, preserving its original standard position angle and magnitude in accordance with whatever chosen scale I use. As you can see, vector A that I've drawn points in the same direction as the vector A on the page in the instructions. And also, my vector A has the same length as this vector A. The directions then say to use a protractor and a ruler and draw vector B to scale, but we want to do it where the tail of vector B is going to be placed on the head of vector A. This was the original location of vector B. What I need to do is I need to move vector B so that his tail is on vector A's head, like this. This is called the head-to-tail method of drawing a resultant. The resultant will now extend from the tail of A to the head of B. The resultant can be called A plus B. It's the result of vector addition. We're now asked to use the ruler and protractor to measure the magnitude of the resultant A plus B. And we have to get the angle of it as well. So measuring the length of the resultant A plus B, I got 7.90 plus or minus 0.05 centimeters. I now have to measure the angle of the resultant. To do that, we'll bring the protractor, and the angle here looks like 77.8 perhaps. Now we have to reverse the order of the addition. Instead of putting B's tail on A's head, we're going to put A's tail on B's head. We're going to move A such that his tail is touching the tip of B. And now we'll draw a resultant from the tail of B to the tip of A. This vector will be called B plus A. And once again, we want to get its length and angle. So for the length of B plus A, I got 7.86 centimeters plus or minus 0.05 centimeters. In order to do the angle of it, I'll bring the protractor back in. And it looks like it's 78.1 or 78.2 perhaps. Okay, there we go. As we can see, the magnitudes are similar for the A plus B versus B plus A method, and the angles are very similar too. It's supposed to be in theory that A plus B and B plus A are the same, showing that vector addition is commutative. The next approach that I'm going to take is to add the vectors together using their components only. This would be a component addition method. The theory is that if we take AX, the X component of A, and add it to BX, the X component of B, that should give us the X component of the resultant. And so AX is the horizontal component of A shown here. The horizontal component of A has to extend from the tail of A to the tip of A horizontally. So it has to go just as far to the right as the tip of A goes. You can make a little projection tracing the tip of A down to the x-axis. And then what we want to do is find this distance here. So I'll measure that now. So I get 3.70 centimeters for this, plus or minus 0.05. What I did was I put a ruler down along this dimension, and I measured that distance from the y-axis to the tip of A horizontally. Now what I'll do is I'll move my ruler over, and we need to measure BX, the X component of vector B. I get 2.13 plus or minus 0.05. We see that AX points to the right. However, BX points to the left. And because of that, we have to make the X component of B a negative. So it'll be negative 2.13 centimeters. Now in theory, what we should be able to do is we should be able to add the components together to find the X component of the resultant. So AX will be replaced with 3.70 plus or minus 0.05. And then BX will be replaced with negative 2.13 plus or minus 0.05. So I get that Rx here would be positive 1.57. And what I'll do is I'll just add the uncertainties together to say that I could be off by as much as 0.10 centimeters. That's just an easy upper bound for the error. Just adding the uncertainties together when you're doing an addition of two measurements. So we'll put that here. Next, I have to measure the vertical components of A and B. So in order to do that, I want to figure out how high off the axis is vector A's head. So you can line up your ruler like this, perpendicular to the x-axis, and figure out how tall is that AY component. I get that AY is 2.64 centimeters plus or minus 0.05 centimeters. And now I'll measure BY, lining up my ruler this way. I think BY is 5.03 centimeters plus or minus 0.05 centimeters. It should be that we can find the Y component of the resultant now by adding AY plus BY, which are the Y components of A and B. So AY was 2.64 plus or minus 0.05, and BY was 5.03 plus or minus 0.05. I get 7.67, and we'll do plus or minus 0.10. Now it says use this component addition method to draw the resultant R on your paper. So basically what I want to do on my paper is I want to go to the right an amount of Rx, and that's going to be 1.57 centimeters. Then I also want to go from there up by an amount Ry, which is 7.67 centimeters. Finally, what I'll do is I'll draw the resultant, which points from the origin here to the tip of where I landed up with Rx plus Ry. And so the black vector is going to be my resultant R. It now says to measure the magnitude, which is the length of the vector R which I had drawn. I'm doing this on my own separate paper. Okay, so first I'll draw my vector Rx, and that needs to have a width of 1.57. Then I'll draw my vector Ry, which has to have a height of 7.67. Then I'll draw the resultant. which points from the origin to the tip of my RY. I'll bring in the protractor now and try to get the angle of the resultant. So it looks like it's pointing toward 77.3. So I believe this is a 77.3 degree angle here. And for the length of it, I get 7.85 centimeters. They ask us now to find the magnitude of R using the formula, where the magnitude can be found by the square root of the squares of the components, Rx squared plus Ry squared. So let's calculate that on the side here. We have to plug in the components 1.57 and 7.67 that we had found earlier. I get 7.83 for my best estimate of R. However, I should also find the largest through a method of propagation of uncertainty. And one of the easiest ways to propagate uncertainty would be to add the uncertainties to the quantities in question. So I'm just going to add the 0.1 to the x component, and then I'll add the uncertainty of 0.1 that I had here. I'll add that to the y component as well, finding the largest possible result for the magnitude. Let's see what that gives us. I get 7.95 for that. Then if we just subtract the largest minus the best estimate, we'll get a good estimate of the uncertainty in R's magnitude. So they could differ by as much as 0.12. And so I'll use that as my uncertainty in the magnitude. So what I'm going to do then is I'm going to say my best estimate of the magnitude was 7.83. But according to these calculations, I might be off by as much as 0.12. So if I did an interval for my magnitude using this method, according to the formula approach of radical Rx squared plus Ry squared, I believe my magnitude is in this range from about 7.71 centimeters up to 7.95 centimeters, where half of the width of the interval is just the 0.12 that I had calculated. Now with the other approach of just measuring, I said it was 7.85 plus or minus 0.05. So that's a little bit more narrow interval. Uh, 7.85 could be here. And here is 7.90 and 7.80. So clearly these intervals are in agreement with each other. Now we have to find the angle of the resultant by measuring. I already did that. It's 77.3 plus or minus, I'll say 0.5 degrees. And now we're supposed to find the reference angle using a formula where we take the tan inverse of the y component over the x component that we had calculated. So 7.67 is what goes on top here, and 1.57 goes down below. Let's see what angle that gives us. 78.4 degrees. However, if we add the uncertainties into the equation, you'd want to do it again, but what I'll do is I'll add the uncertainty in the numerator, but actually subtract the uncertainty in the denominator. The reason being, we want the largest possible numerator now with the smallest possible denominator. That would give us a largest estimate for the reference angle. I get 79.3 now. And 79.3 and 78.4, just subtracting them, the difference is 0.9. So my angle could be off by as much as 0.9. When you're pointing toward the first quadrant with your resultant vector, the standard position angle just is the reference angle. So there's nothing to do here in this case. Okay, so does the formula agree with the measured result? It looks like the intervals would overlap, yes. Let's find the components of R now using these formulas. So I have a magnitude for R that I had measured, 7.85. So I'm going to do 7.85 centimeters times the cosine of the angle. I'll just use my measured angle. And I get 1.73. And then we want 7.85 sine of 77.3. I get 7.66. That's interesting that the x component here did come out a little bit different than the x component that we had measured originally. However, I see that the y component came out just about spot on with matching with what we had measured. Finally, we'll find a percent difference between the graphical approach versus the component approach. So for the magnitude, using the first approach, we had found a magnitude of 7.9. That was with the graphical head-to-tail method. Using the component method, though, we had 7.85. So if I want to do a percent difference, what I would do is first subtract the two. So that was method 1 minus method 2. And then divide by an average of the two. Finally, we'll multiply by 100% to get the percent difference, it's called. I get 0.6% difference for the magnitude. And for the angle, doing it the graphical way, one of my results was 77.8. And doing it the component way, we had 77.3. And again, I get 0.6% error in the angle.